This is Mr. Perry, and this is Forces and the Universe Part 2, and this is Segment 3, where we'll be focusing on light and electromagnetic waves. So, let's get started. Energy waves, or the electromagnetic spectrum. Electromagnetic spectrum waves are transverse waves that carry energy as electricity and magnetism at the speed of light. Now, various types of electromagnetic waves have different frequencies and wavelengths, and together they make up the electromagnetic spectrum. They can travel through a vacuum and through space, and radios, televisions, mobile phones, and radar use signals made up of electromagnetic waves. Light is an electromagnetic wave that can be seen. Other types of electromagnetic waves are invisible. Wave energy, or light. The characteristics of light. Units of light are called photons that can travel through a vacuum and space. Now, light travels in transverse waves and travels fastest in air. Light can travel through transparent or see-through objects like clear glass and water. Light is absorbed or trapped by opaque, which is a not see-through object like walls, and changes into heat energy. Light can be reflected or bounce off from some objects like mirrors, and light can be refracted or bent when passing through some objects like water and prisms. Here's more.
Light. It's all around us. But what is it? Where does it come from? And what does light have to do with color? Light is a kind of energy that travels in waves. It is made when matter is heated up or gains energy. Excess energy is released, in part, as light. This energy is called electromagnetic radiation. When we talk about light, we usually mean visible light, which is the light that we can see with our eyes. But there are more types of electromagnetic radiation that are invisible to us, including radio waves, microwaves, X-rays, and gamma rays. Scientists can detect and measure invisible radiation with special tools. Together with visible light, all these types of radiation are called the electromagnetic spectrum. All electromagnetic radiation travels in waves, but different types have different wavelengths. The wavelength of electromagnetic radiation, or light, is connected to how much energy it has. Light with a longer wavelength, like radio waves, has less energy, while light with a shorter wavelength, like gamma rays, has more energy. Visible light makes up only a tiny part of the electromagnetic spectrum, but it includes every color we can see. The most important source of light here on Earth is the sun. We call ordinary sunlight white light, but it actually includes all the colors of visible light. These colors can be revealed when white light goes through a prism. When light passes through a prism or something like it, it slows down a little bit and bends. Some parts of the light slow more than others, and the light spreads out into the colors of the spectrum. If you want to see all of the colors in the visible light spectrum, look no further than a rainbow. Rainbows are made when water droplets in the air bend sunlight much like a prism. Usually when we talk about a rainbow, we say it is made of 7 colors: red, orange, yellow, green, blue, indigo, and violet. Each color has a different wavelength. Red has the longest wavelength in the spectrum of visible light, and violet has the shortest wavelength. All the other colors have wavelengths in between the two. The colors of a rainbow are always in the same order, because the colors are arranged according to their wavelengths. Red is always on the outside, because red has the longest wavelength, and violet is always on the inside, because violet has the shortest wavelength. Electromagnetic radiation with a wavelength outside the visible light spectrum is invisible to our eyes. Light with a longer wavelength than the reddest red our eyes can see is called infrared light. Light with a shorter wavelength than the most violet we can see is called ultraviolet. When we look at an object, we are actually seeing the light that is bouncing off of it. A green leaf looks green because the leaf absorbs all of the colors in the spectrum except for green, which it reflects. When the green light enters our eyes, our brain tells us it looks green. Things that look white are reflecting almost all of the visible light shining on them, and things that look black are absorbing almost all of the visible light shining on them. Light, both visible and invisible, is all around us. It travels from its source as a wave, bringing energy with it. Without light, there would be no colors. Take a look at the world around you and remember, everything you can see is just different wavelengths of reflected light. Goodbye till next time.
Energy is light waves, visible light spectrum, colors that can be seen by the human eye. Now, different colors of light have different wave frequencies. The longest to the shortest wave color frequencies are, the longest is red, then we have orange, yellow, green, blue, indigo, and violet, which is the shortest wavelength. White color is all the wavelengths of colors, and black is all the color wavelengths absorbed in an object. The color of objects you see is the color that is reflected. We continue with X-rays, which is high energy waves that pass through flesh but not bone. X-ray photographs are used to check people's bones for damage, and in high doses, X-rays can harm people. Gamma rays are the smallest wavelengths and the most energy of any wave in the electromagnetic spectrum. Produced by the hottest, most energetic objects in the universe, such as neutron stars and pulsars, supernova explosions, and regions around black holes. They are very harmful and can cause cancer in humans and animals. And also, as part of the electromagnetic spectrum, we have ultraviolet rays, which are invisible waves that are slightly shorter than visible violet light and carry more energy. We wear sunglasses and sunblock to prevent damage to our eyes and skin by ultraviolet rays. There are infrared rays, which are slightly longer waves than visible red light. We can't see infrared, but we can feel it as heat. When heat energy is transferred by radiation, it is carried by waves of infrared like sunlight. We use infrared light in our remote controls for our televisions. And we have radar. Radar microwaves that have longer wavelengths than visible light. Radar microwaves are used to locate airplanes and ships. Microwaves are used in cooking. Radio waves are the longest waves in the electromagnetic spectrum. They carry radio and television signals around Earth, and radio waves from outer space are picked up by radio telescopes and used in studies of the universe. Check this out.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our Sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
Here we have a look at the electromagnetic spectrum. On our left, you see gamma rays, which are very high frequencies there. And as we move to the right, we have X-rays, ultraviolet, and we can see the wavelengths getting longer. And we have visible light, infrared, microwaves, and eventually on our right there we have radio waves. That concludes this segment of Forces and the Universe, Part 2, This is segment 3, where we've featured and focused on electromagnetic energy.